This is the video for Module 13, Section 7.6, Part 1, about proportions and problem solving. The first thing we're going to talk about is using ratios and rates to write proportions. A ratio is the quotient of two quantities, and the ratio of the numbers a and b can be written three different ways. It can be written as the ratio of a and b, or it can be written as a colon b, or it can be written as a over b. For example, if we have the ratio 5 to 11, we could also write that as 5 colon 11 or 5/11. Here's another example. For a certain college student, the ratio of dollars spent on a car payment to dollars spent on rent was $280 to $700. So if we wanted to rewrite that in another form of a ratio, we could write it as 280 to 700 this way, or we could write it as 280 over 700. And notice in both of these cases that I didn't include the dollar signs. If you think about this as being a fraction, then the dollar sign is a unit, and since we have the same unit in both places, it would actually cancel out. That's one thing about a ratio, is that the units do have to match. And when you write it in a fractional form like this, there are actually no units because they will cancel each other out. Then we also have a rate. This is also the quotient of two quantities, but in this case the units don't match. For example, Allison's new car used 12 gallons of gas to travel 400 miles. We could write this as the quotient of the two quantities to make it a rate, but we could actually write it two different ways. We could put the gallons on top, so that would give us 12 gallons over 400 miles. And if we thought about this as a rate, we could get this down to gallons per mile. The more common way that we think about mileage amounts is miles per gallon. So if we wanted to do it that way, we would put the 400 miles on top and the gallons on the bottom. This way, if we reduce this down, we would end up with miles per gallon, which we're more used to talking about. But what we're going to be doing in this section is solving proportions. And a proportion consists of either two ratios or two rates that are equal to each other. That's why we've been talking about what ratios and rates are. So what we end up with is a rational expression on each side of an equation. So in this example, each one of these two would have either been a ratio or a rate, and we just set them equal to each other. And as we talked about in the last section, if we only have one rational expression on each side of the equation, then we can use our cross multiplication method to solve the equation. So if we have something like a over b equals c over d, then our cross multiplication would say that we were multiplying numerators and denominators across the equal sign. So we'd multiply the b times the c and the a times the d and set those equal to each other. So we end up with an equation that looks like this. A times d equals b times c, and then we can solve that for whichever variable we need to. Let's do a couple of examples. So in these, we're saying that these are proportions just because each one has one rational expression on each side of the equation. And we're going to use that cross multiplication method to solve these. So in this one, we're going to have the 2 times the x and the 7 times the 5, and we'll set those equal to each other. That gives us 2x equals 7 times 5, which is 35. If we're trying to solve this for x, then we're going to divide both sides by 2. So we end up with x equals 35 halves. And over here, again, we've got one rational expression on each side of our equation. So we're multiplying the 2 times the quantity z minus 5 and the 7 times the quantity z minus 3. So we have 7 times the quantity z minus 3 is equal to 2 times the quantity z minus 5. Then in order to solve this, we're going to distribute the 7 on this side. That gives us 7z minus 21. On this side, we're going to distribute the 2. That gives us 2z minus 10. Then we can subtract the 2z from each side. That gives us on the right side just a minus 10 that's left. So now we have 5z minus 21 is equal to negative 10. Then we're going to add 21 to both sides. So on this side, all we have left is the 5z. On this side, we have negative 10 plus 21. That gives us 5z is equal to 11. Now to solve for z, we're going to divide both sides by 5. Now we have z equals 11/5. Now remember, for both of these problems, since we started out with a rational equation, we do need to go back and check solutions, especially to make sure that we're not getting 0 in the denominator. So I didn't show the check for the last one, but I'll show the check for this example. In this one, remember, we want to go back to the original equation to check this. So we're going back to our original equation up there and substituting 11/5 for the z. And again, the most important thing to check here is that you're not getting a 0 in a denominator anywhere. So if we looked at this, if 11/5 and 3 were actually the same value, then we would have a 0 here and we wouldn't be able to use our solution. But since they're different values, that means that this is not going to equal 0. This denominator over here is not equal to 0. So that means that our solution is okay. Now this doesn't, I'm not including a check for arithmetic mistakes here, just for whether the denominator is 0. I'm going to assume that all the arithmetic up here was correct, so that this is our solution. Now we're going to look at using proportions to actually solve problems. So if we have a problem containing ratios, then the first thing we'll want to do is to write the ratios and use variables for any of the quantities that we don't know. Then we'll use the ratios to write a proportion by setting the two ratios equal to each other, and then we'll just solve the proportion. Here's an example. If a 170-pound person weighs 65 pounds on Mars, how much does a 9,000-pound satellite weigh on Mars? So our ratios here are going to compare the weight on Earth with the weight on Mars. So let's write that out over here. So we have weight on Earth weight on Mars. So we have a 170-pound person on Earth. So that's their weight on Earth. Their weight on Mars is 65 pounds. Then we have the satellite, which on Earth weighs 9,000 pounds. And what it weighs on Mars is the quantity that we don't know. This is what actually the question is asking us, is what would this weight be on Mars? So we're going to use a variable here to stand for the weight of the satellite on Mars. Now if we want to write these as ratios, we've got 170 pounds to 65 pounds. So we'll just write that as a fraction. And then our ratio here would be 9,000 pounds to x pounds. So we can write that ratio there. And notice the important thing when you're setting your ratios equal is to make sure that the numerators and denominators match as far as what they're corresponding to. In this one, both of the numerators correspond to weights on Earth. Both of the denominators correspond to weights on Mars. Now that we've got our equation written, we can use our cross multiplication method to solve it. So we'll be multiplying the 170 times the x and the 65 times the 9,000. So that gives us 170x equals 65 times 9,000. If we multiply out 65 times 9,000, would give us 585,000. So we're going to divide both sides by the 170. And if we divide the 585,000 by 170, we get 3,441. This is an approximation because we're rounding to the nearest pound here. So we would end up with our solution being x is equal to approximately 3,441 pounds. Now we do want to go back and check this in our original equation just to make sure, number one, that this doesn't give us a denominator of 0, and number two, that it's a reasonable answer in our situation. So if we go back to our original equation and substitute in 3,441 for x, we're definitely not going to have a 0 in the denominator, so we're okay that way. And if you notice, since in this ratio the denominator was smaller than the numerator, then it should be in this ratio also. That's just kind of a way to check of whether we got a reasonable answer or not. So we could go back and check this by using our 3,441 for x, and we should get approximately the same answer on both sides. And this is going to check. So that means that our 9,000 pound satellite on Mars weighs 3,441 pounds. Now let's look at another problem. In this one, we know that there are 170 calories in 3 peanut butter cookies, and we want to know how many calories there would be in 7 cookies. So again, we're going to set this up as a proportion. In this one, the ratios we set up will be talking about calories to cookies. So this will actually be more of a rate because the units aren't going to match. We're having calories and cookies instead of something like calories and calories. For our first ratio, we have 170 calories to 3 cookies. And for our other ratio, we have an unknown number of calories because it's asking us how many. So let's call that x, since that's our own unknown quantity. So in this one, we have x calories to 7 cookies. Now if we write each of these in rate form or ratio form, this would be 170 calories and 3 cookies is equal to x calories and 7 cookies. Now we can use our cross multiplication. So we're going to multiply the 3 here times the x and the 170 times the 7. And I'm leaving the units in here because that gives us a way of checking at the end whether we solved our equation correctly or not. So we have 170 calories, 7 cookies, and then with the other multiplication we have 3 cookies and x calories. Okay, so we can multiply the numbers here. 170 times 7 is 1,190, and we have calories times cookies here for our units. And then over here we have a 3 and an x, so we have 3x, and we also have the units of calories and cookies over here. So if we're dividing to solve for x, then we're going to divide both sides of this by 3, and since our 3 went with the cookies here, we're going to divide by 3 cookies. So, and what should happen here, and the reason for keeping the units in here, is that you should get your units to cancel out. So we can cancel out the cookies here, we can cancel out the cookies here, and also the 3, of course. And then what we're left with is the unit that we were looking for, which was calories, because we're trying to solve for x calories. So what we end up with here is 1,190 over 3 calories equals x calories. So now we just have to divide by 3, and that gives us 396, I'm going to round to 1 decimal place, 396.7 calories. So the answer to our question of how many calories are in 7 cookies would be there are approximately 396.7 calories in 7 cookies. Now, another type of problem where we end up using proportions is in similar triangles problems. If we have similar triangles, that means that the measures of the corresponding angles in the triangles are equal. And what happens is then that the corresponding sides in the two triangles are in proportion with each other. Here's an example. And similar triangles should look basically the same, just that one is going to be bigger than the other. Although sometimes you have to watch because they can be turned in a different direction, and so it's a little bit harder to tell that they're similar. But these two are meant to be similar triangles. So that means that this angle here would be equal to this angle. So the corresponding angles are equal here. These two angles are equal, and these two angles are equal. That's what tells us that they're similar triangles. So if we know that they're similar, then that means that their corresponding sides have to be in proportion. These two sides, the ratio of these two sides, has to be the same as the ratio of these two sides so that we get a proportion. So we can write those two ratios in order to find the unknown length that we're trying to solve for, the y. So we know that 5 meters over 12 meters, which is our ratio of these two corresponding sides, should be equal to y meters over 10 meters, which is the ratio of these two sides. And notice again that whatever you choose to put in the numerator of these two, they have to come from the same triangle. So notice that the 5 meters and the y both came from the smaller triangle, and the 12 meters and the 10 meters both came from the larger triangle. Now we can use, and we can actually cancel out our units here. So we have ratios here instead of rates. So we just have 5 over 12 is equal to y over 10. Now we can do cross multiplication. So we're going to multiply the 12 times the y and the 5 times the 10. And set those equal to each other. So this gives us 50 equals 12y. If we divide both sides by 12, then we're going to get 50 twelfths is equal to y. If we reduce this to lowest terms, that would give us 25 over 6. So depending on how the question is asked in the homework, you might be asked to leave this as a fraction, or you could put it in decimal form. If we divide 25 by 6, we get 4.17. This is rounding to 2 decimal places. So the length here would be approximately 4.17. And again, you should go back and check your answer in your original equation. If you notice back here, our denominators already just had numbers, no variables. So there's no way we could get a 0 denominator here. The other thing you want to look for is whether this is a reasonable answer. And again, if you compare the two triangles, the leg on the bottom here was just a little bit shorter than the leg on this side. So this value should be a little bit less than this one. That's just checking to see if you got a reasonable answer or not. Okay, let's look at this pair of triangles. And again, the way these are drawn, these two are meant to be similar triangles. So that means the ratios of the corresponding sides should be equal so that we get proportions. And here we're supposed to find the unknown length x. So let's set up one of our ratios so that it has the x in it. So let's do the x and the 28, since those would give us one ratio. And then we can pick either of the two sides since we know both of the values of the other two sides. So this time let's pick this side to look at. So that would give us 12 over 14. And again, it doesn't matter which way you set this up as long as these match. So notice that these two lengths both came from the smaller triangle, and these two both came from the bigger triangle, and everything corresponds there. So now we're going to use cross multiplication. So that gives us x times 14 is equal to 28 times 12. If we multiply this out, we've got 14x is equal to 336. Now if we divide both sides by 14, that gives us x is equal to 24. So again, we want to go back to our original equation and make sure that this doesn't give us a 0 anywhere in the denominator. And we already had constants in our denominator, so that's not a problem. Now we want to see if this is reasonable. And notice that in this triangle, the side on the bottom was the longest side, so it should be also in this triangle. So this looks like a reasonable answer. Now the next type of problem we're going to look at is a number problem. And for this, we will have to do a lot of translating from words and phrases into expressions and equations. So this table gives you some ideas of different words that translate into the 4 operations and into equals. So we've got several that translate into addition, subtraction, multiplication, division, and then several different words or phrases that translate into an equal sign. Okay, so if we have a problem like this, the first thing that we want to do is translate from the words into expressions and an equation. So let's read all the way through the problem first. We've got 5 times the reciprocal of a number equals the quotient of 2 and the difference of the number and 3. And then we're supposed to find the number. So since it talks about a number several times in here, let's go ahead and set a variable for that. So let's let n equal the number. We could use any variable we wanted to. We could use n, x, y. I just decided to use n here. Now we're going to translate. So if we have 5 times the reciprocal of a number, let's just start with that part. Okay, well we know our number is n. If we have the reciprocal of that number, so let's take our phrases and take them out of here. So the reciprocal of a number, if our number is n, that would be, the reciprocal would be 1 over n. So we've got that part is 1 over n. And then we're going to take 5 times that whole thing. So, and 5 times is just 5 multiplied by. So 5 times that is going to give us 5 times 1 over n. Now we have the equals, and that just translates into an equal sign. And then we're going to have the quotient, which signals division, of 2 and something else. Let's take this whole phrase and set it off because we're going to have to translate this one first. So we have the difference of the number and 3. Remember, our number is n, so the difference of the number and 3 would be n minus 3. So we're taking that, and then we have the quotient of 2 and that difference. This is where it gets a little bit tricky, is figuring out what order to do all these in. So we've got the quotient of 2 and the difference. Well, we've already got the expression for the difference. So this would translate into 2 divided by our n minus 3. Okay, so we've got our two expressions that we found. So we have 5 times 1 over n. Then we had our equal sign. And then we had our quotient, which we found over here. So now we have a whole equation written. Let's make this a little bit easier to look at just by going ahead and multiplying this. So we have 5 over n equals 2 over n minus 3. And by doing that, we can see that we actually have a proportion. We only have one rational expression on each side, so we can use cross multiplication. So we have 5 times n minus 3 is equal to 2 times n. If we distribute our 5, we have 5n minus 15 is equal to 2n. If we subtract 2n from both sides, then we have 3n minus 15 equals 0. Then if we add 15 to each side, we get 3n is equal to 15. Dividing by 3, we end up with n is equal to 5. Now let's check our solution. So first we're going to go back to our equation that we started with here. So we have 5 times 1 over 5 is equal to 2 over 5 minus 3. So here we have 5 times 1/5, that's going to be 1. And over here we get 2 over 2, which is equal to 1. So that checks. So that means that this is our solution. And since we started out with a problem in words, then we need to write out our answer in words. We can just say the number is 5.
Let's do one more example. In this problem, we have if 3 times a number added to 5 is divided by the number plus 9, the result is 4/3. Find the number. So let's start by assigning a variable for our number. So let's say let n equal the number. And then we're going to translate this sentence into an equation. So first of all, if we have 3 times a number, that would just be the same as 3 times n, or 3n, since n is our number. Then we're adding that to 5, so that would give us a plus 5. So that whole quantity is divided by something else. So let's put a fraction bar there. It's divided by the number plus 9. So this would be n plus 9. That's going to be our whole denominator here. So back to our problem, then we have the result is 4/3. The result is the same as saying it's equal to. So over on this side we have 4/3. Now we've got our whole equation written, and we can use cross multiplication in this one since we just have one rational expression on each side. We're going to multiply the 3n plus 5 times the 3, and then the n plus 9 times the 4. With both the 3n plus 5 and the n plus 9, we need to put those whole expressions in parentheses because we're multiplying the whole thing times something else. So we have the 3n plus 5 in parentheses times the 3 is equal to the n plus 9, again in parentheses, times the 4. And we could write each of these in the opposite order if we wanted to. So we could move the 3 so that it was in front of the 3n plus 5 and the 4 so that it was in front of the n plus 9. Now we need to distribute the 3 and distribute the 4. So here we have 3 times 3n plus 3 times 5. On the other side we have 4 times n plus 4 times 9. That gives us 9n plus 15 on the left side and 4n plus 36 on the right side. Now let's subtract 4n from both sides. That leaves us on the right side with just 36. If we combine our terms on the left side, we have 5n plus 15 is equal to 36. Now we can subtract 15 from both sides. Let's continue this up here. So that gives us just 5n on the left side and 36 minus 15 on the right side. And 36 minus 15 is 21. So now if we divide both sides by 5, that gives us n is equal to 21/5. Now let's check our answer. And remember, first of all, since we started out with a rational equation, we have to check and make sure that this solution doesn't give us 0 in one of our denominators. So we're going back to our original equation and substituting the 21/5 for the n. So here, since we have 3 times a fraction, we're just multiplying the 3 times the numerator of that fraction. That's going to give us 63/5 plus 5 on the top, and we have 21/5 plus 9 on the bottom. So on the top, if we get a common denominator between those two, it would be 5. That means we need to multiply the 5 here times 5 over 5. That gives us 25/5. And the same thing on the bottom, our common denominator would be 5, so we're going to multiply this 9 times 5 over 5. That's going to give us 45/5. So on the top we have 63 plus 25, which is 88/5, and on the bottom we have 21 plus 45, which is 66/5. Here, since we're dividing by a fraction, we can actually take this up here and flip it over, so we can make it 5 over 66, and that turns it into a multiplication. So that's going to give us 88 times 5 over 5 times 66. And if we cancel our 5's, and we can cancel 22 from both the 88 and the 66, so that would give us a 4 here and a 3 here. So that ends up being equal to 4/3. And so this checks. Our solution is that the number is 21/5.